Hey everyone, welcome back. Today we're going to be following up on the previous videos that I've been making about developing and running Z80 assembly language and machine code programs on for the Mattel Aquarius computer. And in the first two videos we took a look at two different methods that allows us to do that. The first method, we used actually a tool for the Sinclair Spectrum computer, which is the ZX Spin development environment. And we used that to create our Z80 assembly language program and assemble it into machine code. And the second method we took a look at, we used a basic loader program to manually poke the machine code bytes into memory and execute them for us. Now, in those two programs, what they had in common was we were the ones choosing where in memory those machine code bytes or our machine code program would be stored. So today we're going to do something a little bit different. We're going to look at, well, a couple different methods, which are actually two versions of the same method really, where the computer is actually going to determine for us where exactly our machine code program will be stored in memory. And it's going to accomplish that by looking at the variables section in memory, where it reserves certain places in the RAM to store its variables, in particular variable arrays, as well as the string variable buffer. And we'll get into all that in just a moment. But one thing to take note of for today's method is that, as I mentioned in the first video, there are two different ways you can create a machine code or assembly language program. And one method makes a program that's relocatable, and another method would make a program that's not relocatable. So a relocatable program means you can load it anywhere in memory and it will still execute properly. A non-relocatable program, which uses specific memory addresses for jumping and branching, it would rely on specific memory locations for branching properly to different sections of the code. And so that type of program would not be relocatable. And since today's methods are going to be using a location in memory that we're not aware what that specific location is, because the computer will be determining it for us, today's methods would only be suitable for programs that are relocatable, I would think. So in any case, it's still quite interesting to take a look at these methods and see a different way of making machine code programs for our Mattel Aquarius computer. So let's go ahead and take a look at it right now. Okay, let's go ahead and get started. And we're going to, first of all, I think before we start, we should discuss exactly what it is we're trying to accomplish. So we're going to be using a program that is very similar and almost identical to the programs we looked at in our previous video. But in today's video, it's a bit different because, as I mentioned in the preamble, the computer is going to be choosing where in memory to store our machine code program for us. So there's two different methods we're going to be looking at today. And you can see on my screen, the first method is called variable array. Oh, actually, I put them both in this title. I'm just going to erase this one because it's a kind of a spoiler alert. But anyway, you've seen it already. So we're going to be looking at two different methods. One is the variable array method, and the other is the string buffer method. So I'm just going to delete this part for now because we'll be looking at that a bit later. And both of these methods, as it shows here, can be used on an unexpanded Aquarius, meaning we're not relying on the micro expander or MX functionality in order for this method to work, particularly because we're not relying on the expanded amount of RAM or expanded memory, and we're not relying on special commands that are only available in USB BASIC, which comes installed with the micro expander or MX. So these methods can be used on a regular unexpanded Aquarius, or of course with the Aqualite emulator in non-micro expander mode. And they can also be used in expanded micro expander mode if you like, or they can be used with a Mattel Aquarius that has a micro expander or an MX as well. All right, so the two methods we're going to be looking at today are going to be using the area in memory that the computer uses for storing variables. And we're going to use that space not for storing variables, but for storing our machine code program. And so if we're going to be using these areas for storing a machine code program instead of storing variables, then obviously if we're running a basic program at the same time, for example, if we're using a basic loader program to run a part of a program that executes our machine code subroutine or program, then we're not able to use this method for storing the variables that it was intended to be used for. So for example, in this first method here, which is called variable array, we're going to be dimensioning an array, as you can kind of see in our first line here that says line number 10, dim m50. Well, that dimensions a numeric array, and that memory that's reserved for that array is going to be used for our machine code program, meaning we can't use this method for storing actual variable arrays as it was intended for. So we don't want to try to mix up actual variable arrays with our machine code program in the same basic program. So just keep in mind that we have to use these different memory areas for one or the other. We can either use them for storing the variables they were intended to, or we can use them for storing our machine code program. And of course, today we're going to be using them for storing a machine code program. So let's go ahead and take a look at how exactly we're going to accomplish this. But before we get into the programming code that I have on the screen here, let's go back again and take a look at the system variables that I mentioned in a previous video. And as you probably know, the system variables are the internal variables that these computers use to keep track of different things that it needs in order to operate. And I'm going to be using the same resource that we took a look at in the previous video for examining the system variables, the vdstenoven.com website. And in particular, let me just resize it here. You can see that we're looking at the memory layout section of this website. And the memory layout section shows us how the memory is allocated, including where the system variables live. So let's go ahead and just take a look at this now and see if we can figure out where we want to store our machine code program. So here we go. If we take a look at these addresses here, you can see that it shows you the different memory addresses. Here it starts at 0000, which is obviously the lowest memory address that we took a look at in the memory map. And it just shows the different sections of memory that's pre-installed in a regular unexpanded Aquarius. So this section here from 0000 up to 2FFF, it says it's not addressable with peek and poke. So we're not going to be using that area. And then it shows this area here from 3000 to 37FF. It says video and color matrix. So this is the area in the computer that is used for storing the values that will show up as characters and colors on the screen. So we don't want to use this memory area as well. And let's take a look at the next section here. So the next section here says 3800 to 38FF, system information. And we're not going to use that area either. And we're going to be looking at the next area here that says 3901, start of basic program code. So the way the memory map is laid out is it has the basic program that we would type in, and then it has some extra stuff after it, namely variables, that we're going to be looking at in a second. So this is where the start of the basic program code lives at 3901, apparently. And we're not going to be putting our machine code program there because that's where our basic program is going to live. And let's just keep going and take a look. It says here the next section is called Start Simple Variable List. So this is where the variables now get stored above where the basic program lives in memory. And let me just move this over a bit because we want to take a look at this next section here. So this is the section we're interested in here, the Start Array Variable List. So this is the area in memory where the computer stores array variables. So when we dimension an array variable or a variable array, it's going to store it in memory, or rather it's going to reserve space in memory for that variable array, and that space is where we're going to be storing our machine code program. So obviously, if we're going to be storing a machine code program in this location in memory, we're going to need to determine where this location is so that our program can store its bytes of machine code there. And it tells us exactly right here how to determine that. It says the pointer to this start address, which would be the start of our variable array reservation space in memory, it says it can be found at 14552 and 14553. And I'm just going to bring over now the ROM disassembly page that we looked at briefly in a previous video. Right here. And I'm also going to look at our calculator right here. And you can see that this value in decimal of 14552 represents a hexadecimal address of 38D8. And I want to look that up in the ROM disassembly to see what is stored at that location. So 38D8 is the address we're interested in, which is right here. Let me just zoom in a bit on this. Right here, 38D8, and it says pointer to beginning of array table. So this address here, 38D8, which is labeled as pointer to beginning of array table, this corresponds to this number here, 14552. So these two addresses, 14552 and 14553, together they contain a 16-bit address, which equals the address where the start of the array table is located. And that's what we're interested in, because we're going to be storing our machine code program in the space that's reserved for a variable array. So we need to know, in this case, where the array table starts. And we simply do that by extracting the values from these two addresses, 14552 and 14552. Well, I think there's a typo here, actually. 14552 and 14453. So this should actually be 14552 and 14553. So just keep that in mind. It looks like there's a typo on this page. And it looks like probably if I keep going down here, this next section seems to have a typo as well. 14554 and 14455. That should be 14555. Anyway, so the two addresses we're interested in are 14552 and 14553, and we're going to extract the value that's stored in those two addresses, combine it together into another address, which will tell us where the start of the variable array table begins. So let's go back to my program here, and you can see those two addresses in my program right here. Right here, 14552 and 14553. So what this line of code does is simply extract values from these two memory locations. And the first one here, 14553, that's our high byte, so we multiply it by 256. And then the other one, 14552, that's where the low byte is stored, so we don't have to multiply that by anything. We simply extract that as it is. And if you use this formula, AD equals peak 14553 times 256 plus peak 14552, that will give us a number that equals the address where the variable array table starts. And I'm just simply putting that into this variable called AD for address. And we'll just jump back to our first line of code so we don't forget what that's doing. Our first line here is reserving the space in memory for our machine code program by dimensioning an array variable. In this case, I just chose the variable m. It could be any variable you like, but here we're dimensioning the m variable array with 50 elements. And you can see my note here, it says reserve 50 elements for numeric array m. The start of this array space will be the address to store USR machine code routine. So the start of this space is where we're going to be storing our machine code program. You might be wondering, well, how much space does this actually reserve for us? Is it reserving 50 bytes? Well, it's probably not reserving 50 bytes, because this is actually reserving, as you might be aware of already, a dimension statement like this. In this case, it's dimensioning a numeric variable array, and that means it's going to be storing numbers. And in BASIC, numbers usually require more than 1 byte of memory to store them, particularly signed numbers that have floating point decimals. So let's just take a look at our emulator, and we're going to see exactly how much memory this is going to reserve for us, and see if it's any more than 50 bytes. Alright, so here we have the wonderful Aqualite emulator on the screen now, and I'll press enter to return into basic mode, and you can see it's just operating in the regular unexpanded Aquarius mode right now without the micro expander function enabled. And here we are in basic, and I'm just going to use the free command to see how much available memory we have right now. So I'll type print free open brackets 8, and you can use whatever character you like within the brackets. I like to use the number 8 just because it happens to be on the same key as that left bracket. And if I press enter now, you can see we have 1724 bytes available to us. So what happens if we dimension an array now, and we'll see how much available memory is left after we reserve space for this variable array. So let's type dim a, and then let's just assign 10 elements for this a variable numeric array, just like that. And so now the computer has reserved space for this numeric array. And let's see how much free space we have available now. Print free 8. And now you can see it dropped from 1724 down to 1673, which if I do the calculation on a regular calculator here, so 1724 minus 1673 equals 51. So even though we reserved space for a numeric array variable that contains only 10 elements, the computer actually reserved 51 bytes of memory for us. So that's one thing to be aware of, is the number inside this bracket here, which indicates the number of elements you're reserving for the array, is not the number of bytes that you're reserving for your machine code program. It will be more, as you can see here. All right, so let's go back now. And here we are back at the program. And let's go through it again. And we're still on the first line, but that's okay because most of the rest of the program we've seen in our previous video. So I'll just be skimming through that rather quickly. So in the first line 10 here, we've dimensioned a numeric variable array with 50 elements. So let's go back to our emulator and see how much space that will reserve for us. So I'll go back here and I'm just going to type clear to wipe out all the variables, and I'll type print free again. 1724, and now I'll dim M 50 and print free, and it dropped from 1724 to 1513. So in this case it reserved more than 200 bytes for our machine code program, which will be more than enough. Alright, so let's go back to my program here. And the first line of this program dimensions the M variable array, which as we now know will reserve a couple hundred bytes of memory for us. And in the next line here, we already looked at this formula that extracts both the high and low memory portions to tell us where this array lives in memory. And we store that in a variable called AD. And then in these next lines, you can see they're exactly the same as what we looked at in our previous videos. We're calculating the high byte for the start of the machine code address. We're calculating the low byte for the start of the machine code address. And then we're poking those high and low bytes into these addresses here, 14340 and 14341, which is the system variable that the computer uses to execute this USR instruction down at the bottom here, which actually runs our machine code program. And if you're not familiar with how these instructions work, then you might want to go back and watch my previous video where I went through this in detail and explained exactly how this system variable works to allow this USR function to operate. And in the first video that I made, it explained exactly how this program works, as well as this USR function, how it operates with this system variable. And in the second video that I made just before this one, I showed how we can pass a value into this USR routine, which is pretty cool because our machine code program can then use that value for whatever purpose it wants. So in today's video, we're using these same codes to set up that system variable, which allows this USR function to operate. And that's what these lines of code here do. And now starting at line 65 here, we're setting up a for next loop that loops from 1 to 6 because our machine code program is going to contain 6 bytes, which we've hard coded down here in these data statements. You can see there's 3 data statements. Each one represents a different assembly language instruction right here, showing on the right. So in line 200 here, these 2 numbers in the data statement represent the machine code bytes that are equivalent to this Z80 assembly language instruction LDA 25, which loads the value of 25 into the A register. And then our second line here, which says data 50048, those are the 3 machine code bytes that correspond to this assembly language instruction LD brackets 12288, comma A, which loads whatever values in the A register into this memory address 12288, which as you saw from our previous video, corresponds to the video location on the screen, which fills the border with whatever character we poke into that address. And then finally, we have our return statement here at line 220, data 201, which is the machine code byte for the return instruction. So this program, what it does is it loads a value of 25 into the A register. 25 corresponds to the little robot symbol in the Aquarius computer. We're loading that value into the memory address 12288, which will fill the entire border with that character symbol. And then we simply have our return statement. So this for next loop that we're setting up here for f equals 1 to 6, first thing it does is it reads a byte of our machine code program and puts it into this variable called bt. Then in our next line 80 here, it pokes that value into our current address for our machine code program, which starts at AD, which we loaded up here in line 20, AD. And then after it pokes it into that address, it increments that address to prepare the computer to load the next machine code byte into the next address. And then it simply cycles through the loop with this next F instruction at line 105. So all this program does here is it's doing the configuration setup that we needed to do to make this USR subroutine work. It extracted the address in memory where this variable array is being stored, because that storage area is where we're going to be loading our machine code program into. And then after it does all that, finally here in line 1000, we actually execute our machine code program by running this USR function. So x equals USR 0 in this case. We're not passing it any variables or any values, so the number between these brackets can just be 0. And this line 1000 will execute our machine code program. And then finally we just have a stop statement at the end. And now that we know that line 10 here has reserved a couple hundred bytes of available memory for us by dimensioning this array variable, and it's going to store our machine code program into this space that's reserved for that array variable, then it should be able to execute our program from that place where it's stored in memory. So let's go ahead and copy these lines of code. So there's our program now. So now if we run this program, it should fill the border with that character that has a value of 25, which is the little robot symbol. So let's go ahead and try it now. There you go, that works perfectly. So what it's doing is it's taking our machine code program, it's storing it into memory that has been reserved for this numeric variable array, and it has automatically extracted the location of that array by using that system variable, or those two addresses that point to that location, which is these two addresses here, 14552 and 14553. So all we need to do to use this method is simply dimension a variable array that is large enough to store all of our machine code bytes, and we can run this program and we've got our machine code program working. So that's pretty cool. Now the next method we're going to take a look at is almost identical to this method, but it just has a slight twist. So let's go back to our memory layout page here, right here, and you can see the addresses that we used were 14552 and, well, 14553, which is allocated as the start of the array variable list. So now what we want to do is go and use this location here, which is start string variable memory. And it says the pointer to this start address can be found at 14411 and 14412. It says default 50 bytes can be enlarged with the clear command, e.g. clear 100. Now if that's all very confusing to you, I did actually cover this in the video that I made about basic variables on the Aquarius. And this storage area in memory is for something called the string buffer. And let's just take a look at this location on the disassembler listing as well. So 14411, if I convert that into hexadecimal, 14411, you can see here 14411 in decimal converts to 384B in hexadecimal. So let's look that up on the disassembler page, 384B. All right, here's our disassembler, and we're looking for 384B now, which is right here, 384B, and it describes it as top location to use for the stack initially set up by init according to memory size to allow for 50 bytes of string space changed by a clear command with an argument. So that didn't really clear it up for us very well, as much as I was hoping it would. But anyway, what this is doing is this Mattel Aquarius computer has something called a string buffer, and a string variable, you're probably aware, is something like a string. If I go back to our emulator here, I can type new and then a string equals hello, print a string, and it prints hello. So a string variable is an alphanumeric variable. It contains alphanumeric characters, just like this a string. It prints the word hello in this case. So the way the Mattel Aquarius computer works is it reserves a certain amount of space in the computer for all of the string variables in your basic program. So if you have, let's say, 50 bytes available, then you can only have a total number of 50 characters in all of your string variables in your entire basic program. And so the way we can check that is we can do, instead of typing a print free X or print free number like we did before, so remember we did print free 8. For example, that gives us the amount of free bytes in RAM memory. Well, now I just want to see how many available bytes do I have for our string buffer. And to do that, I type print free, and then this time there's two ways I could do it. I could type a letter inside of quotations, or I could type a letter followed by a $sign. So I'll do it that way. I'll just type a string, and it could be any letter you like. So print free a string and close bracket, and you can see it says 45. And what we can do is change this string buffer size to whatever we want, and we can use that area to store our machine code program as well. So let's say I use the clear command here, and I type clear 100. This should reserve 100 bytes of memory for our string variables, but if we don't assign any string variables, we could use that space to store our machine code program. So let's check this available space now that we've used the clear statement, and we'll type print free, and then let's say a string again, and it says 100. So now we should have 100 bytes of available memory for us to use for our machine code program. So let's take a look at our next method now, which is right here, and I'm calling it the string buffer method. And again, it says it can be used on an unexpanded Aquarius. And this time, instead of dimensioning a variable array in our first line, we're using that clear command to reserve a certain number of bytes for our machine code program. And this clear command would normally, as I just explained, it would reserve a certain number of bytes for our string variables. But in this case, we're not going to be using it for string variables. We're going to be using it for a machine code program. So this is what we do initially, is to use the clear command to reserve a certain number of bytes for us in that string buffer. And then in our next statement, this instruction is very similar to the one in our last example, but now we're using two different addresses because these two addresses point to the location in memory where this string buffer starts. It actually points to the start of the stack, and if you're familiar with the stack, how the stack works, well, if you're familiar with it, I don't need to explain it, but if you're familiar with the stack, it starts at a certain address in memory and it counts down. So the top of the stack would be just underneath where this string buffer lives. And this address pair here, 14411 and 14412, points to the start of the stack, or the top of the stack, which is also the bottom of where the string buffer lives. Now, to be perfectly honest, I'm not sure if you might need to adjust this address a little bit. In Z80 assembly language, pushing a value onto the stack would push it into the top of the stack, and then it would count down. So I'm not sure exactly if these two addresses point to the top of the stack or the bottom of the string buffer. So we may need to adjust these values up and down a bit, because in this program I'm not actually pushing anything onto the stack to test out if this works when the stack gets manipulated or not. But since my assembly language or machine code program is not using the stack, then it shouldn't matter in this particular case. But just be aware that these two addresses are the system variable that point to the top of the stack. So it may need some adjustment, it may not, I'm not 100% sure. I haven't played around with it that much, but I still wanted to share this method with you. So let's go ahead and try this program now. And it's using exactly the same assembly language program, the same machine code bytes. The only difference is, instead of storing our machine code program in an area of memory that's reserved for a numeric array, it's storing it into a location in memory that's reserved for the string buffer. So let's go ahead and copy this code and put it into our emulator. And there we go. Not sure what that bracket is at the end there. Let me just do a listing. Okay, so here's our new program, which is using the string buffer area to store our machine code program. And again, it's using that same robot character symbol that has a value of 25. It's going to poke that into that hidden line at the top row, and it should fill the border with the robot character if all goes well. So let's give it a try here. And there you go, that worked as well. So both of these methods work by automatically calculating where in memory to store our program. We can either store it in space reserved for a numeric array, or we could store it in space reserved for the string buffer. And like I said, we might need to play around with it a little bit depending on how the stack exactly gets used with this system variable. But the method seems to work fine for my examples, and I just wanted to share that with you. So now we have two more methods we can use for storing machine code and running it on our Aquarius computer. All right, so now we've taken a look at three different methods, actually kind of 3.5 different methods we can use for creating and running Z80 assembly language and machine code programs on the Mattel Aquarius. And keep in mind, of course, I'm not an expert on any of this stuff. I'm just kind of playing around with it and learning what I can and seeing what seems to work and sharing my information with you as I go along. And you can try it out for yourself and maybe you'll find even better ways to use it. And so this is what I've learned so far, and I think it's a good start. It's encouraging to be able to even get even a simple assembly language or machine code program running for the Aquarius. And in my next video, I'm going to share with you the probably most comprehensive setup that I've decided I'm going to try using for making machine code programs for the Aquarius, at least initially. And just to prepare you, if you haven't watched the first video in this kind of series where I went over all the technical information about the Mattel Aquarius memory map and the ROM disassembly and the system variables and all that stuff, and the way the characters get displayed on the screen and the hidden top row and everything, all that stuff you'll need to know in order to, well, do any of the stuff that we're talking about in these videos. So if you haven't watched the first video in this series, you might want to go back and take a look at that, unless you're already familiar with those topics. And as always, thanks for watching, and we'll see you next time.